Hello, everyone. I hope you all hear me well, and I hope you all see my screen. First of all, I would like to welcome you all to our Hyperscanning Summer School. We are very happy that so many researchers from all over the globe registered to this event that officially will start today. First, a bit an introduction of myself. I'm Sophie. I work as an application specialist at Artinis, so I'm responsible for sales and support. I was in contact with most of you regarding the hyperscanning, also probably with some of you regarding other customer-related questions. And today with me is my colleague Katharina, who helped me with organizing this hyperscanning summer school. So today's meeting is a relatively short meeting. It is basically an introduction meeting and also a kickoff meeting for the Hyperscanning Summer School. In the first part, we will introduce functional near-infrared spectroscopy, or fNIRS, really shortly. And in the second part, we will give an introduction to hyperscanning, what it actually is, for what it can be used. And we will, of course, also explain the reason of the Hyperscanning Summer School that we organized this year. So we will start with a very short introduction of us, or Artinis Medical System, as a company. So Artinis is a NIRS company that develops and distributes fNIRS devices since 2002. We are based in the beautiful Netherlands in the middle of Europe, and we are a middle-sized company and have approximately a bit over 60 employees now. So we develop NIRS and fNIRS devices for both muscle and brain measurements. So we sell devices worldwide and serve all markets that use NIRS to measure muscle and brain, for instance, in the sports and the neuroscience field. In 2023, we acquired TMSI, which is also a Dutch-based company producing EEG and HD-EMG devices. And we were very happy about that because that gives us the room to increase our portfolio and also to increase the options in measuring muscle and brain activity. Also, very quick introduction to the Hyperscanning Summer School itself. So this summer school is organized in the framework of our launch of the Bright Ultra system. You will hear a bit more about the Bright Ultra system and why it is so special later in the talk, but also during the Bright Ultra demonstration that we organized on the upcoming Mondays. So if you're interested in that, definitely feel free to join the sessions, which are live demos where you also have the opportunity to ask all kinds of questions. Another aim of the Hyperscanning Summer School is to show the versatility of hyperscanning to study group interaction. To do this, we have different talks by experienced researchers in the field of hyperscanning. We are also very happy to introduce our keynote speaker, Dr. Pascal Friedricher from the University of Essex, who will tomorrow and the upcoming Thursday give 2 keynote talks on fNIRS hyperscanning, starting from the data acquisition over the post-processing, going on to the analysis of hyperscanning data. We will also have live demonstration of our Bright Ultra system, as already mentioned, where we showcase the device and how it can be used in naturalistic settings for large group measurements. A few practical information before I start with the part of the theory of functional near-infrared spectroscopy. So this is a 10-day program and we have 1 session each day. They vary in time. You are registered to all of them and I hope to see as many of you at each talk as possible. All these sessions will be held on Teams and most of the sessions will be recorded. We will always give an introduction at the beginning to the talks, where we will also mention which talks are actually recorded and which not. And all the talks include a question and answer at the end. So we will read out your questions to the researchers that popped up during the webinar sessions. If you would like to get a certificate of attendance, this is available on request. Just message us at askforinfo@artinis.com. And if you have any questions regarding to hyperscanning or other questions related to fNIRS that come up after the webinars, please also feel free to contact us at askforinfo@artinis.com. So much to the practical information. So let's now start with the fun part and a small introduction to functional near-infrared spectroscopy. So the theory of near-infrared spectroscopy is based on two main principles. The first one is that our skin is relatively transparent to near-infrared light. And the second one has to do with the absorbance criteria of two different chromophores, which are near-infrared which are oxygenated and deoxygenated hemoglobin. And basically, with NIRS, what we do is we measure the changes in light absorptions of a volume of a tissue, and from those we can measure or calculate the changes in the concentration of oxy and deoxygenated hemoglobin. As I already mentioned, the absorbance criteria of oxy and deoxyhemoglobin are one of the backbones of the NIRS technique. So the optical window for near-infrared light, as you can see on the graph on the right, goes from 7 to 900 nanometers. In the visual spectrum, which is before from 400 to 700 nanometers, the main absorber is biological tissue. And in the wavelength over 900 nanometer, the main absorber is water, which you can see here as the yellow line in the graph. But in this optical window for the near-infrared light, the main absorbers are oxygenated hemoglobin, which you can see here in red, and deoxygenated hemoglobin, which you can see here in blue. So basically our devices, they emit lights in two different wavelengths to detect the changes in oxy and deoxygenated hemoglobin. We use 760 nanometer for deoxygenated. As you see, it peaks quite nice around 760 nanometer. And we use 850 nanometer to detect oxyhemoglobin. So I mentioned at the beginning, we basically measure the optical density changes, and from those we calculate the concentration changes. And to do so, we use something that is called the modified Lambert-Beer law. So first, before I'm going to explain the formula a bit in detail, let's have a look at the graph that you can see on the right, on the left. So when we use fNIRS, we have transmitters and receivers placed on the scalp, usually in a difference of approximately 30 millimeters. The transmitter transmits the light. This light is scattered back by oxy and deoxyhemoglobin and is then received by a receiver. And as a rule of thumb, the measurement depth is approximately half of your inter-optode distance, so half of the 30 millimeters in between transmitter and receiver. So let's now have a look at the modified Lambert-Beer law. So of course, on the one side, you have the changes in optical density, also absorbance. The formula for that is the incoming divided by the outgoing light. And as our tissue is heterogeneous, we add a base at the beginning of that. And this equals the extinction coefficient of each wavelength times the concentration of oxy and deoxyhemoglobin times the physical path length, which is the 30 millimeter in between transmitter and receiver, times something that is called the differential path length factor. So right now on this picture, you see that the transmitter transmits the light as a very straight line. However, in reality, due to the heterogeneous nature of our tissue, the light looks more like a banana shape due to the scattering effects. And this DPF is included to correct for the scattering effect. So now if we look at the formula, we have the extinction coefficient, the physical path length factor, the physical path length, and the DPF, which are all constants, but we have the changes from optical density and the changes from concentration. So using this formula, we go from the physical absorbance to the actual biological measures that we would like to receive. So now that you know the general theory behind near-infrared spectroscopy, let's focus on fNIRS, functional near-infrared spectroscopy, which basically is used to measure changes in the concentration of oxy and deoxygenated hemoglobin in the brain. And the special thing is these changes can be measured quite locally, so you can basically, you can assess the changes in between one receiver and one transmitter. So a bit on what or how this response for fNIRS actually looks when a brain region gets active, or what kind of a response we would expect. So I will explain this on an example. A very commonly task used in finger tapping, used in fNIRS is the finger tapping task. So basically I'm tapping the fingers of my left hand and I measure over my right motor cortex, which usually gets active during this task performance. And what we then see with oxy and deoxygenated hemoglobin is that we have an increase in oxygenated hemoglobin and a slight decrease in deoxygenated hemoglobin happening after approximately 5 to 7 seconds. And once I'm done with performing my task, both of these values go back to baseline. This is called the hemodynamic response. Maybe some of you have heard that from the bolt response before as well, because with fNIRS we measure basically the same as we do with fMRI. So now that we know how the response looks, maybe it's good to have a short look on why this response actually comes in place. So once a brain region gets active, there are two different mechanisms happening. The first one is the neurovascular coupling. This leads to an increase in cerebral blood flow, and therefore we have an increase in the oxygenated and a decrease in the deoxygenated hemoglobin. At the same time, there's the neurometabolic coupling. So the oxygen metabolism is increased, which leads to a slight decrease in oxy and a slight increase in deoxy. And if we take these two mechanisms together, we come and end up with the typical hemodynamic response. So basically, there's an increased metabolic demand and oxygen consumption, which leads to an increased blood flow. And then once we are done with the performance of our task and once this neuroactivity leaves, then the concentration goes slowly back to its baseline. So now we heard a bit about the background of fNIRS and NIRS in general. And the second part of this presentation is focusing on a very quick introduction to hyperscanning. And of course, the first important question to answer here is, what is hyperscanning actually? As probably most of you know, hyperscanning is a neuroimaging technique that is used to record brain activity of two or more individuals at the same time during a social interaction or during the performance of a joint task. And hyperscanning can be used to study the neurodynamics underpinning social interactions in different situations. So for instance, in collaboration, in competition, but also during communication. Hyperscanning recently gained a lot of attention and also spanned into a lot of different application areas. The first and probably most basic one is its use in social neuroscience. So basically to understand the neurological backgrounds during social interactions, for instance, during communication or during empathy. It can also be used in cognitive neuroscience, therefore most often to understand the cognitive functions and coordination of action during the performance of social interaction or social tasks. Further, it is used in developmental studies to study the neural mechanisms of social interactions in infant and children. So this can be done in either peer-to-peer interaction or in the interaction with parents or other caregivers or adult participants in general. It is also possible to use hyperscanning in a bit more naturalistic settings, for instance, during education, so in classrooms, to assess the interactions between teacher and student, and here to understand if traditional teaching or collaborational teaching can improve the interbrain synchrony of the subjects. It is also more and more used in clinical research, here basically to understand the brain mechanism in diseases that come with symptoms that influence social functions, for instance, depression, ADHD, or schizophrenia. And it is also used to assess the interaction of clinicians or therapists with the patient to see if there's a good communication and to see if the therapy can be improved. And a bit more uncommon and outside of the box, fNIRS is also used during performance of arts, for instance, during dancing or also during playing music in orchestra and bands to assess the interbrain synchrony of groups. So fNIRS is a technology that has a lot of advantages, and these advantages are also especially helpful in the use of hyperscanning. fNIRS is, for instance, completely portable and comfortable. So basically, often the devices, or especially our devices, are lightweight. They all weigh less than 300 grams, and they allow for free movement and for complete portable setups. Further, fNIRS is relatively easy to use, especially compared to other neuroimaging modalities, and it is also quick to set up. And compared to, for instance, fMRI or EEG, it is relatively insensitive to motion artifacts. And if we take these major advantages of fNIRS together, it is especially suitable for the use in sensitive participants, so it allows for hyperscanning also in clinical settings, but also in infants. So it basically can include any kind of participants. And it also allows for the performance of measurements in naturalistic settings. So basically, it helps to bring the brain activity measurements from the lab in outside and real-world scenarios, which for hyperscanning and in general studying social interaction is a quite important criteria. So now we've learned a bit more about hyperscanning itself. And the definition. The history of hyperscanning is relatively new, but there are some milestones in that history that we would like to point out here, or that stand out in general and that are good to mention. So the term hyperscanning was first introduced in 2002 by Montague and colleagues. They published a paper in Neuroimage where they performed a simultaneous measurement of two participants in two different fMRI scanners, and they managed to synchronize these two fMRI scanners. Then in 2006, so then from 2002 to 2006, hyperscanning was already used predominantly in fMRI research. However, starting off around 2006, also the first studies using EEG hyperscanning were introduced. And one study to mention here, which is seen as a pioneer study quite often, is the study of Barbioni and colleagues. Especially because they used EEG hyperscanning in a more naturalistic setting. So basically, they measured in groups of 4 that played a card game. So both in a competitive but also in a collaborative setting. And they could show higher coherence in the players that were in the same team compared to the players in the opposite team. Then in 2009, Lindenberger and colleagues achieved the first discovery of a statistically relevant increased interbrain synchronization during a real-time EEG hyperscanning. So basically they measured on 2 guitar players which played the same melody. This is seen as a milestone, especially in the history of EEG hyperscanning, and this is also until now one of the most cited papers in EEG hyperscanning. In 2011, then the hyperscanning of fNIRS was actually introduced, and the first fNIRS hyperscanning study was published by Fuane et al. So they did a task of a synchronized button press, so basically where 2 participants had to press the button at the same time, and they could find an association between the increased covariance in the prefrontal region of each subject and an increased behavioral coordination. Around a similar time, Cui et al. Published a paper where they also used fNIRS hyperscanning, but in a bit more of an unconventional use. So basically, instead of using 2 different fNIRS machines, they used one fNIRS machine and split it over the 2 participants. So each of them received half of the optodes. So in the years from 2011 to 2017, more and more researchers included hyperscanning to study social interaction in their portfolio using both fNIRS and also EEG. But most of them were focusing on smaller groups or D8s of 2. And in 2017, there was the first classroom hyperscanning study done using EEG in a large group and also bringing the technique from the lab setting into a naturalistic setting, and therefore taking the approach to the next step. This paper by Dicker et al. Basically measured measured interbrain synchrony using EEG at 12 students at the same time, and that over a course of a complete semester. And they also developed a complete new analyzing approach for neural coherence, which is based on group level. And this study can also be seen as a validation study for large group hyperscanning in naturalistic settings. A few more stones on the way. In approximately 2018, also the use of a parent-child fNIRS hyperscanning was introduced. Therefore, one of the first papers to found was done by Reindl et al. They performed a study where kids did a competitive and a cooperative task together with their parents, but also together with a stranger adult. Then, of course, EEG has its advantages. Also, fNIRS has its advantages, but both of them are very often combined to achieve the best of both worlds, which we call multimodality. And in the recent years, fNIRS EEG or multimodality measurements were also used more and more in a hyperscanning setup. For instance, in a paper by Fronda and by Coney, They measured fNIRS and EEG at the same time during exchange of gifts, and they found significant increased brain synchrony during and after the gift exchange. Then very recently in 2025, also the first classroom hyperscanning study using fNIRS was published by Feng et al. They measured in the teacher and also in students during a traditional teaching approach, but also during an unconventional teaching approach that included more collaboration. They actually used our Pride system, and they measured in 8 and also in 16 students, which can be now seen as a validation study also for the hyperscanning of classroom fNIRS. So this all leaves us to the question, hyperscanning advanced quite a lot in recent times. What could probably be the next step? So in our opinion, this would be to bring this hyperscanning in the lab in the naturalistic setting, and also to be able to perform this in large groups. And therefore, we have worked on our Pride Ultra system, which is the first and only mass fNIRS hyperscanning system in the world. We put plenty of work in that, and we are really proud to launch it this summer, as it can, in our opinion, help to push the limits of hyperscanning research and enable a whole new world, especially for large group interaction in naturalistic social settings. The Pride Ultra allows for hyperscanning in up to 30 participants at the same time using our Pride light systems. It can measure from any cortical brain region, and it can be applied in various naturalistic settings and applications. So during the next days, you will hear more about the Pride Ultra, especially therefore I invite you again to join the sessions on the upcoming 2 Mondays. You will also hear more about hyperscanning itself. This is the literature list. And with that, I would also like to end my talk for today. I thank you all again for registering. We look very forward to hear more about hyperscanning in the next upcoming 10 days. Again, we are very happy that you all registered, and we hope that you learn a bit or learn a lot more about the technique, also about how our devices can help with hyperscanning. And I would also like to point out again that tomorrow we will have our first keynote presentation. So Dr. Pascal Frantica from the University of Essex will tell you in a first part of his talk more about the theory and the experimental design for fNIRS hyperscanning experiments. So we already look forward to see all of you there. And with that, I would like to end the session for today. I wish you all a very nice day, and hope to see you all again tomorrow.